Hi class, this is part 2 of section 6.4. Okay, so we're going to continue to use this fact, y equals log base a of x, if and only if a to the y power is equal to x. Okay, so if we go back and think about the exponential growth functions that we talked about in the last section, okay, starting with y equals 2 to the x, the inverse of y equals 2 to the x is log base 2 of x. And we see that the ordered pairs that were on the exponential growth function are switched and they become points on the logarithmic function. So for example, 3, 8 is the 0.83 on the graph of its inverse. 2, 4 is the 0.42 and so on. Okay, we had negative 1, 1/2. That switches to 1/2 negative 1. Okay, also our exponential functions have a horizontal asymptote at the x-axis, so the line y equals 0 is a horizontal asymptote for our exponential function, so in this case our exponential growth function. And then notice the inverse of that, our logarithmic functions have a vertical asymptote at the y-axis, so that's the line x equals 0. Okay, so based on the graph of our logarithmic function, we can see that we can only plug in positive values for x. So the domain is from 0 to infinity. And the range is all real numbers. This should make sense because the domain of our exponential function is all real numbers, but the range is only from 0 to infinity. And we know that the domain and range of functions and their inverses are switched. Okay, so for example 4, we want to graph the function y equals log base 3 of x. We'll sketch the graph and then also determine the range of the function. So logarithmic functions are unique because normally to graph them, if we want to find ordered pairs that are on the graph, it's easier to switch your logarithmic equation, switch it over to an exponential equation. So this is the exponential equation, 3 to the y power is equal to x. Okay, and now we have 5 y values that we can plug in as the exponent, and we'll find the corresponding x value. Okay, so 3 to the negative second power, we'll write that as 1/9. 3 to the negative first power is 1/3. 3 to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. Okay, so now we have 5 points that we can plot. I'm going to start with the one in the middle, our x-intercept. So we have the point 1, 0, also 3, 1, and 1/3 negative 1. Okay, so these 3 in the middle are the 3 that I'm really looking for if I ask you to graph the function and label 3 points. Okay, 1/9 negative 2 is fine, but it's really hard to tell where 1/9 is on the graph. Okay, and then 9, 2 is going to be too far to the right. Okay, so it's probably going to be off your grid. Okay, so also it's important that we know what's happening as we get closer and closer to the x-axis, so it needs to be clear that our graph is approaching, I said the x-axis, I meant the y-axis, that the graph is approaching the y-axis, but it never gets to it. Okay, since we have a vertical asymptote at the line x is equal to 0. So our graph approaches it, but never touches it or never crosses it. Okay, the domain, 0 to infinity. So a parenthesis again, a parenthesis because we do not include 0, so only positive numbers. And then the range is all real numbers. The logarithmic function does grow off to infinity, but it just does so very slowly. Okay, next is y equals log base 5 of x. So we'll do the same thing. Let's rewrite this exponentially. So 5 to the y power is equal to x. And then we have 5 values to plug in for y, and we'll find the corresponding x value. Okay, so the reason why we do this is because if you try to pick values for x, you're probably not going to pick ones that work out nicely. Okay, so you'd have to know what numbers to plug in ahead of time to know what x values to pick. So doing it this way, we don't need to worry about that. Okay, so if y is -2, I would have 5 to the negative second power, which is 1 over 25. 5 to the negative first is 1/5. 5 to the 0 power is 1. 5 to the first power is 5, and 5 squared is 25. Okay, and again, I'm going to concentrate on these three guys here in the middle. Okay, so again, starting with the x-intercept of 1, 0. I'm going to go out to 5. 5, 1 is another point on the graph, and then 1/5, -1. Okay, so this is what I'm looking for on your graph. If it's just a standard logarithmic function that hasn't been shifted or transformed at all, -1, 0, and 1 are points on the y-axis. You will have the x-intercept, our base is 5, so we have the point 5, 1, and then 1/5, -1. Okay, so those numbers will obviously depend on the base. Okay, but your graph should look something like this, not too much there so that whomever is looking at the graph can read it and understand what numbers are there. Okay, let's label the vertical asymptote. So that's x is equal to 0. Okay, so again, it has to be clear that the graph is getting closer and closer to the y-axis, but it never touches it. Okay, the domain is again 0 to infinity, and the range is all real numbers. So these other points, again, you'd have to go all the way out to 25 before we're up at 2. Okay, so the graph grows, but it does so very slowly. Okay, example 5. So same idea, we're going to state the domain, sketch the graph, and then determine the range, but now we also want to find the inverse of the function, and we'll state the domain and range of the inverse function. All right, so f of x is equal to log base 5 of x minus 2. Okay, so we actually just did y equals log base 5 of x. So if you want to graph these by transformation, you're more than welcome to. This x minus 2 would move our graph, let's see, to the right 2 units. Okay, let's start off with the domain. So whatever we plug into the log function has to be positive. So this means that x minus 2 must be greater than 0, which means x has to be greater than 2. So the domain is from 2 to infinity. Okay, we could even put this vertical asymptote on our graph right now. So the vertical line x equals 2 is our vertical asymptote. Okay, next let's rewrite our function. Okay, so I'm going to actually replace the f of x with y. So y equals log base 5 of x minus 2. And now I'm going to rewrite this as 5 to the y power is equal to x minus 2, which is equivalent to 5 raised to the y power plus 2 is equal to x. Then we would pick our y values, so -1, 0, 1, and then maybe 2 depending. Sometimes that'll fit on your grid. Okay, and we'll find the corresponding x values. Okay, so if y is -1, I would have 5 to the negative first power plus 2. Well, 5 to the negative first power is 1/5. So I'm just going to write this as the mixed number 2 and 1/5. Good. Next, the exponent is 0. So I have 5 to the 0 plus 2. 5 to the 0 is 1 plus 2. So the corresponding x value is 3. 5 to the first power plus 2 is just 5 plus 2, or 7. And then 5 squared plus 2, this would be 25 plus 2, or 27. Okay, so we gave it a shot, but 27 too is going to be off the grid. Okay, so we just have 3 points that make sense to plot. Let's start with 3, 0. So that's our x-intercept. 7, 1. So that's a little bit, I'm going to switch to green. So 7, 1 is a little bit off the graph, but it would be right there. And then we also have 2 1/5, -1. Okay, so just a little bit to the right of that vertical asymptote. Okay, so make sure that as you graph the function, it looks like we get closer and closer to that vertical asymptote. Okay, we're going down to -infinity. And we do increase, but we increase pretty slowly. Have to go all the way out to 27 before we're up at 2. Okay, good. Now for the inverse, we have actually done all the work for the inverse, but I'll do it again just in case you want extra practice. Okay, so the way that we've found the inverse before still works. Okay, so the first step is to replace f of x with y. So y equals log base 5 of the quantity x minus 2. We would then switch the x and the y. So we have x is equal to log base 5 of y minus 2. At this point, you have to know to use that property that changes logarithmic equations to exponential equations. Okay, so this is equivalent to 5 to the x power is equal to y minus 2, and now we can add that 2 over. So 5 to the x power plus 2 is equal to y. So this is my inverse function. Okay, so when I said we've really done all the work, it's because we have it up here. So I did the work when I was trying to graph the function, because again, for logarithmic equations, it's easier to graph them if you write them exponentially. Okay, so I had my logarithmic equation and I wrote it exponentially. The only step I didn't do is to switch the x and the y. Okay, and that's what's done over here. Okay, so y equals 5 to the x power plus 2. Okay, whereas if we don't switch the x and the y, this would give us the graph that we wanted, really the logarithmic graph, right? 5 to the y power plus 2 is equal to x. Okay, the domain we have, the range, again, all real numbers. Put the domain here too. The domain was 2 to infinity. So that means that for my inverse function, those domain and range will be switched. Okay, let's see, I'll graph in red. We can even graph this exponential growth function. So it's been shifted up 2 units. So that's our new horizontal asymptote. So I know it'll go through the point 0, 3. It'll go through 1, 7. Okay, so this x equals 2, that was the vertical asymptote for the first graph, not for the red graph. Okay, the red graph has this horizontal asymptote at the line y equals 2. Okay, and again, the domain and range are switched. So the domain for our exponential function, which is the inverse in this case, is all real numbers, and the range is from 2 to infinity. Okay, so here I'm going to go through them one more time. So I rewrote my equation. This way I can pick y values to plug in as the exponent. And I find my corresponding x values. Okay, I then also found the inverse. Okay, so just going through the steps again. If you understand that we've already done the work, just switch the x and the y and you're done. Otherwise, you're going through the steps like we always do. Replace f of x with y, switch x and y, and solve for y. Okay, good. And then here's our, in black is this logarithmic function. Okay, the domain and range are given, and we have in red our exponential growth function. Okay, so again, exponential growth function's domain is all real numbers, so this does eventually cross this vertical asymptote. The vertical asymptote in black only applies to the logarithmic graph, which is also in black. Part B is similar. This time our function is y equals log base 2 of x plus 12. So let's start off by finding the domain. Remember that what we input to the log function must be positive. So x plus 12 needs to be greater than 0. So x will be greater than negative 12. The domain is negative 12 to infinity. Okay, now let's try to graph the function. So I'm going to rewrite this f of x as a y. So we have y equals log base 2 of x plus 12. Let's rewrite this exponentially. So 2 to the y power is equal to x plus 12, and then subtract the 12 over. So 2 to the y power minus 12 is equal to x. So again, we have this time 4 y values. We'll plug those in for y and find the corresponding x value. All right, so y is -1, so we have 2 to the negative first power minus 12. So 2 to the negative first power is 1/2 minus 12. That's going to give us -11.5. Next, we're plugging in 0, so 2 to the 0 power is 1, so we have 1 minus 12, or -11. 2 to the first power minus 12 will give us -10, and then 2 squared, or 4 minus 12, so -8. Okay, so now we have 5 points to plot on our graph. Finding the inverse. So again, we've done all the work to find the inverse, but if you were unsure, replace f of x with y. So we have y equals log base 2 of x plus 12. Switch the x and the y. So x equals log base 2 of y plus 12. And then rewrite the equation. So 2 to the x power is equal to y plus 12. And finally subtract the 12 over. So 2 to the x minus 12 is equal to y. So this is our inverse. F inverse of x is the exponential function 2 to the x minus 12. Okay, so again, we did the work back here. The only thing we didn't do was switch the x and the y. So you could just come back here, switch the x and the y, and then you have the inverse function. Okay, so now we'll graph them. Starting off with our vertical asymptote. So the domain of our log function is -12 to infinity. So we have a vertical asymptote at the line x is equal to -12. Let's see, 10, 1, and 8, 2 are nice numbers to plot because they don't involve fractions. And then we also have, oh, sorry, I didn't do 10, 1, I did 10, 0. Okay, so 10, 1, 11, 0, -11.5 was down at -1, so it would be right there. Okay, so again, having 3 or 4 points is not going to be enough unless you know what the graph looks like, right? So it has a vertical asymptote at x equals -12, and then it increases, but it does so pretty slowly. Okay, so so as long as your graph goes through those points and has the correct shape, you're good. Okay, the domain, we have -12 to infinity. The range, again, is all real numbers. So now we have the domain and range for our inverse function. The domain is all real numbers, and the range will be -12 to infinity. Okay, so here's the graph of our logarithmic function and the graph of our exponential function on the same coordinate system. Okay, so notice that our exponential function shifted down 12 units, but it's still exponential growth. I wanted them on the same coordinate system just so you could see that it's a reflection about the line y equals x. So if I could fold the screen along this diagonal line y equals x, the logarithmic function and our exponential function would match up. Okay, one last thing I want to talk about in this video is what happens if instead of having exponential growth, like y equals 2 to the x, what if we start off with exponential decay, something like y equals 1/2 to the x power? Okay, so it's still a one-to-one function. Exponential decay is still 1-to-1, right? So there's still an inverse function. So it would be our log function with the base of 1/2. Okay, so when your base is a fraction, it looks pretty different than if the base is a number like 2 or 3, 5, or 10. Okay, it's still a reflection about the line y equals x, but it's a little bit harder to see. I think it's pretty clear to see when you have exponential growth. So if your base is a number bigger than 1, and then log base, in this case log base 2 of x, right? It's easy to see that they're a reflection. Let's look at the exponential decay function as we go towards that horizontal asymptote. If I took this portion of the graph and flipped it along that line y equals x, I would come up here and again be going towards the vertical asymptote. Same thing here, so this portion of the graph, if you folded it, would match up with this portion down here in the fourth quadrant. Okay, so it is still, they're still inverses of one another. You could graph y equals log base 1/2 of x in a similar way that what we've been doing. But for this class, what I want you to focus on is being able to graph logarithmic functions when the base is a number bigger than 1. So our graphs will look something like this. Okay, increasing functions. For the exponential functions, you will need to know, you will be tested on both exponential growth and exponential decay. Okay, good. I know this is a lot, so there's one more video still on graphing, and then you'll have lecture questions after that.